Welcome to Tomorrow Unveiled, the program that cuts through the noise and provides you with the most crucial breakthroughs shaping the future, distilled from the last 7 days of intensive research. For a long time, the conversation around artificial intelligence has been dominated by the interface, how well it chats, how quickly it summarizes text. But this past week confirmed something far more profound. We are, I think, officially beyond the era of just sophisticated chatbots. We are at a true inflection point where AI is fundamentally transitioning into autonomous agents. These agents are capable of complex reasoning, planning multi-step processes, and taking serious action, whether that's digitally within complex enterprise software or physically in the real world through robotics.
Absolutely. And that autonomy, that capacity for high-level reasoning and decision-making with, minimal human oversight, that's precisely the core theme of this week's data. Our mission for this deep dive into the information compiled by our dedicated research team is really to examine the highest corroborated and newest breakthroughs. We're focusing specifically on systems moving toward integrated, autonomous, reasoning, and collaborative capabilities. And this isn't a slow evolution. The velocity of this shift, well, it's reshaping enterprise, fundamental scientific research, and critical infrastructure. It's happening right now.
Okay, let's unpack this. It feels, well, monumental is the word. We should probably start where the immediate commercial impact is greatest.
Yeah.
The digital enterprise. Because, like you said, it feels like this technology has moved almost instantly from a theoretical lab concept to foundational business infrastructure.
It absolutely has. And what's fascinating here, really, is the sheer velocity and, maybe even more, the coordination of market entry. Our research shows a simultaneous kind of synchronized launch of enterprise-ready agentic AI platforms across all the major players. We're talking about Google's Gemini Enterprise, OpenAI's AgentKit, and Microsoft's Co-Pilot Studio. They're all hitting general availability with production-ready agent infrastructure basically at the same time.
Right, that coordination is critical. If everyone's launching together, how do companies even begin to evaluate the real differentiation? Like between Google's Agent Space, that's what Gemini Enterprise was, right?
It's the rebranded agent space, yes.
Yeah.
Unified platform now.
Okay, so Agent Space versus Microsoft's Copilot Studio. Is this just going to be a race to the bottom on price, or are there fundamental capability differences we need to, understand?
That's a really crucial question. And the data strongly suggests it's a race for capability, definitely not just price. Think about it. Previously, an AI assistant might handle a single task, maybe generate an outline or draft an email. These new agentic systems, though, they're designed for complex, multi-step problem solving. They can initiate a task, reason about the necessary steps, access multiple external tools, maybe databases, and complete the entire workflow autonomously. So the differentiator really becomes how well they handle those complex internal workflows and how smoothly they integrate with external systems.
Okay, complex problem solving. It can sound a bit academic. Can you give us a tangible example? Something with quantifiable value that companies are actually seeing right now from these new multi-step agents.
Certainly. Let's look at Google Gemini Enterprise. It's being positioned as the new front door for AI in the workplace, basically unifying conversational AI with these pre-built agents and giving them access to enterprise data. A really clear, corroborated example our team found is Virgin Voyages. They deployed a Gemini agent specifically designed to write marketing copy and, importantly, orchestrate campaign assets across different channels.
Orchestrate, so not just writing.
Exactly. And the result? They reported a massive 40% reduction in the time required for campaign creation.
40%, that's transformative for a marketing team. But how? How did the agent actually achieve that? Was it just drafting text way faster, or was it doing more like the strategic optimization part?
It was handling the entire multi-step process. That's the key. The research indicates the agent didn't just generate the first draft. It managed asset assembly. It handled tone adjustments based on demographic targets. It even initiated A/B testing variations and ensured compliance with brand safety guidelines. These are all tasks that previously required multiple human touchpoints, sign-offs, back and forth.
So it's the coordination overhead. The agent takes care of that.
Precisely. That's where the bulk of the time savings come from. It's the agent handling the project management, essentially.
That makes the shift from chatbot to agent crystal clear. It's the difference between doing a task and, managing a project. What about Microsoft? They've been pushing Copilot everywhere. What does the new Agentic Co-Pilot Studio bring to the table that's different?
So Microsoft Copilot Studio is now at general availability, and the key differentiator highlighted in the research seems to be its autonomous agents that feature deep reasoning and critically robust computer use capabilities. This means the agents can perform external UI automation.
External UI automation, you mean, like clicking buttons on the screen?
Exactly. They can literally interact with external systems and applications just like a human user would. Clicking buttons, navigating menus, inputting data, following complex enterprise workflow templates.
Wow. So it's not just relying on APIs, which might not exist for older systems. It's visually navigating a screen, mimicking how a person uses a desktop.
Precisely. And that's critical for legacy systems, or maybe custom enterprise tools that don't have easily accessible APIs. The agent reasons its way through the graphical user interface. And the adoption figures are interesting too. We know over 230,000 organizations are already using Copilot Studio in some capacity. Plus, Microsoft's strategic move to consumption-based pricing, well, it suggests they're anticipating this infrastructure being adopted right across the enterprise stack. They want to make it economically accessible to automate huge numbers of internal tasks.
Okay, so we've got agents optimizing marketing campaigns, automating UI workflows, really fundamental business processes. But what about the higher stakes areas, like security? Can we actually trust AI agents to secure the very systems they're living inside of? That seems complex.
It is complex, and this is where the research points to a really significant qualitative leap in autonomous defense capabilities. Our sources detail a new system from OpenAI called ARDVARK. It's powered by GPT-5, apparently, and focused specifically on autonomous security research. You have to understand, traditional vulnerability detection tools are mostly static. They check code against known bad patterns, or they use something called fuzzing.
Right, fuzzing, just throwing random stuff at it to see if it breaks.
Pretty much. Random data, hoping for a crash. Aardvark is fundamentally different.
How so? How does its reasoning approach change the security game?
It moves beyond simple pattern matching to something more like path planning. Think about how a human security researcher works. They don't just look for known bad functions in isolation. They reason through potential exploit paths. They chain multiple steps together, consider dependencies, the whole context. Aardvark tries to mimic this methodology. It uses advanced reasoning and tool use capabilities to analyze code structure, identify potential weaknesses, and then autonomously simulate multi-step exploits to actually verify if a vulnerability is real.
That's a huge shift. So the AI isn't just checking the code based on a list, it's actively thinking and operating like a skilled red teamer, autonomously hunting for these complex vulnerability chains. That's impressive. Are we seeing similar agentic shifts in content governance? Because that's obviously a massive challenge for platforms dealing with user-generated content.
Yes, and it's addressing a key problem in content moderation: agility. The research team flagged the introduction of these new GPT-OS safeguard models specifically for dynamic content moderation. The really novel paradigm here is that instead of relying on fixed policies that are baked into the model through extensive and, frankly, very expensive training, policies that often become outdated the moment some new harm emerges online.
Yeah, they're always playing catch up.
Exactly.
Yeah.
So these models, which are available in pretty large parameter sizes like 120 billion and 20 billion, they use dynamic developer-supplied policies that are applied right at the moment of inference.
Wait, so you can update the safety policy in real time, essentially, without having to retrain the entire gigantic model. That would definitely address the lag inherent in traditional moderation.
Precisely. It allows for much more agile and nuanced governance, which is especially important in, rapidly evolving linguistic and cultural contexts online. However, this flexibility and the rigor you need for these high-stakes decisions, it comes with a significant cost. And that brings us to a critical operational challenge that the research really highlighted: the computational cost of safety.
The cost of safety. Tell us more about that. How much are we talking?
Well, our sources indicate that these safety reasoning systems, the layers that are performing those alignment checks, applying the policies, doing the vulnerability assessments we just talked about, they can consume up to 16%, 16% of the total compute resources in production deployments.
16%. Just for the safety check, that sounds like a staggering amount of overhead. Why is it so high? And what are the operational consequences of that kind of expense?
It's high because ensuring safety isn't trivial. It often requires a secondary, sometimes equally powerful reasoning agent just to evaluate the primary agent's intended action and output against a complex, nuanced policy set. It's like having a supervisor AI watching the worker AI. And 16% is definitely not trivial. It highlights a critical operational tightrope for companies. They're constantly forced to balance performance, latency, and cost against safety. If you try to shave off compute to save money or make things faster, you might inherently be compromising the rigor of that safety check. This cost is a really critical constraint on how fast and how widely these complex agentic systems can truly scale.
That's fascinating. So the relentless drive for efficiency is now directly colliding with the absolute necessity for security ethical operation.
Yeah.
Wow. Okay, let's pivot slightly. We've talked enterprise security. Now let's look at a frontier where autonomous reasoning seems to be generating potentially revolutionary concepts, scientific discovery. We're talking about AI not just processing data, but actually generating entirely new, novel research ideas. Is that right?
That's exactly right. And this brings us to a really fascinating development detailed in the research. The Virtual Scientist System, or VRSCI, this is an LLM-based multi-agent system, specifically designed to mimic collaborative human scientific teamwork. It's not just crunching numbers, it's simulating the dynamic, often messy, iterative process that human researchers go through when they're trying to generate novel hypotheses.
A multi-agent system mimicking a research team.
Yeah.
How does the synthetic collaboration actually structure itself to achieve novelty? What's the process?
The process described is quite meticulous, broken down into 5 core steps. First, there's collaborator selection, where the system assembles agents based on their simulated expertise and even their past collaboration history, like picking the right people for a project team. Second, topic discussion, where these virtual scientists debate and select a focused area of inquiry. Third is idea generation, where they propose concepts, refine them, build on each other's suggestions. Fourth, and this is crucial, novelty assessment. They compare the generated ideas against vast databases of past and contemporary research papers to see if it's actually new. And finally, abstract generation. Once a high novelty idea is selected, the system turns it into a format that looks like a publishable abstract.
That's an incredibly detailed simulation of the academic life cycle. But what did the study actually find about the optimal way for these agents to work together? I'm really curious if they suffer from the same dynamics as human teams. Like, did bigger teams or just endless debates automatically mean better, more novel ideas?
This is probably the most surprising and maybe the most human insight from the findings. While increasing the team size definitely boosted novelty initially, more diverse ideas, more expertise in the virtual room, the research found that the optimal novelty score was consistently achieved with a moderate team size, specifically 8 members and 5 discussion turns.
Wait, seriously? So AI agents can suffer from virtual groupthink? Or maybe just too many cooks in the kitchen? Or even meeting fatigue? It's genuinely fascinating that the same constraints we see in human collaboration, the coordination overhead, finding that sweet spot, seem to apply almost perfectly to these LLM agents.
It really does mirror that human reverse U-shaped curve for team performance, doesn't it? The research suggests that excessive size, or just too many discussion turns, led to coordination challenges, diminished creativity, the outcomes started to resemble cognitive fatigue, or maybe settling on less innovative ideas just to reach consensus. That moderate size seems to provide the maximum benefit without incurring those paralyzing costs of too much overhead.
Incredible. And how are they validating that these generated ideas are truly novel and not just, sophisticated rearrangements of existing knowledge or random noise?
They use rigorous metrics, and importantly, these metrics were validated by human researchers. The metrics are basically twofold. First, historical dissimilarity. How different and potentially disruptive is the idea compared to research published in the past? Second, contemporary impact. How similar is the idea to cutting-edge research being published right now? This suggests relevance and potential influence. And the VRSCI system demonstrated a genuine capacity to generate ideas with high novelty scores on both counts. The research mentioned examples like new approaches to robot-assisted cancer treatment, things like that.
So in the digital realm, we have autonomous agents running parts of our enterprises, securing our systems, and now even generating the next wave of scientific theory. It's a comprehensive shift.
Yeah.
Now let's pivot to where this intelligence meets the physical world embodiment.
Right. We're definitely witnessing the convergence of this agentic AI with actual hardware. And the most compelling example of this transition right now, according to our research team's analysis, is the rise of general-purpose humanoid robotics, really led by Tesla Optimus.
Optimus, yeah. It's been in the news quite a bit, but what makes the current iteration and, I guess, the commercial vision behind it a true breakthrough? Why isn't it just another cool but ultimately niche lab prototype?
I think the key breakthrough context here is scale and general-purpose utility. That's what the research points to. Optimus is being positioned as the first credible pathway towards mass-produced, general-purpose humanoid robots, moving beyond those highly specialized prototypes designed for just one task in a very controlled environment. It's already undergoing extensive public testing and iteration, which signals a clear intent to scale commercially, and probably quite quickly. This robot is designed from the ground up to learn and perform tasks across diverse environments, like manufacturing, logistics, maybe even potential consumer use down the line.
Okay, let's talk specifics on the hardware, especially the dexterity. You mentioned in the outline something about 22 degrees of freedom in the hands. What does that actually mean in practical terms for what the robot can do?
Yeah, that detail is significant. It's really the difference between a robot that can just grasp a uniform heavy box and one that could potentially perform fine assembly tasks. Most current industrial robots might have, say, 3 to 5 degrees of freedom in their end effector, their hand. A human hand is incredibly complex, 27 bones, tons of articulations. Optimus's hands reportedly boast 22 degrees of freedom, plus another 3 in the wrist and forearm. That level of articulation enables tasks requiring near-surgical precision. It means the robot could potentially manipulate small, irregular objects, use complex tools designed for humans, maybe even thread a needle eventually. And this advanced dexterity, crucially, is powered by the same AI backbone used for their full self-driving cars, integrating vision and neural networks for real-time spatial mapping and control.
And the commercial ambition seems to match that technical complexity.
Absolutely. The target price point mentioned is ambitious, somewhere between $20,000 and $30,000. That range is critical because it aims squarely at consumer and light industrial scale, not just those ultra-expensive, highly specialized industrial niches. And the long-term vision is, frankly, staggering. Scaling production eventually to 1 million units annually. If they get anywhere close to that, it puts a potential timeline, maybe within the next 12 to 24 months, on general-purpose robots starting to enter manufacturing floors, logistics centers, and maybe even the home. The impact on labor and productivity could be massive and potentially very rapid.
This whole shift into the physical world, it requires more than just sophisticated hardware, right? It relies heavily on these advanced reasoning models we've been talking about to translate digital plans into complex physical actions in the real messy world.
It absolutely does. And our research highlights the rise of what are being called embodied reasoning models for robotics. Google DeepMind, for example, is working heavily in this area. Agentic reasoning is the critical bridge here. It's what enables robots not just to react to immediate stimuli, like seeing an obstacle, but to plan complex multi-step processes across time and space. For instance, figuring out how to retrieve a specific item from a cluttered shelf that involves perception, planning, navigation, manipulation, identifying which tool to use for a task, and how to manipulate that tool in a novel environment it hasn't seen before. These models can even integrate external digital tools like searching the internet for instructions on how to fix something to inform their physical actions. That's the very definition of autonomous, intelligent physical action.
That really is the convergence, isn't it? AI designing science and AI designing physical motion. Speaking of science, let's delve a bit deeper into how AI is fundamentally changing the core of scientific research itself, specifically the relationship highlighted in the research between AI and the mathematical and physical sciences, AI plus MPS. You mentioned it's a profound two-way street.
It really is a deep symbiotic relationship. We're talking across math, physics, chemistry, materials research, astronomy, fundamental sciences. On one side, as we touched on with VRSCI, AI is dramatically accelerating scientific discovery in ways that traditional computation, even supercomputers, simply couldn't manage before.
Can you detail some of the specific mechanisms there? How exactly is AI accelerating science in these incredibly complex fields?
The research points to several key mechanisms. First, something called simulation-based inference, or SBI. This is absolutely crucial for complex models, where traditional statistical methods often fail because the likelihoods, the probabilities involved are mathematically intractable, just too complex to calculate directly. Think about refining cosmological models that involve dark matter, or analyzing complex particle physics events from colliders. The sheer number of variables can overwhelm conventional math. AI inference techniques can draw robust conclusions even from these intractable systems.
Okay, so solving the intractability problem, that's huge. What else?
Second, AI is used to accelerate simulations by creating highly efficient surrogate models. These are essentially AI models trained to mimic the behavior of a much larger, slower, high-fidelity simulation. So instead of running, say, a multi-week simulation of a complex chemical reaction, the AI surrogate model might provide a highly accurate prediction in just minutes. This is essential for problems that require thousands or even millions of iterative queries, like searching for the optimal composition of a new material or drug molecule. Third, it massively enhances pattern recognition and anomaly detection. finding those crucial needles in the haystack in the enormous data sets generated by modern scientific instruments, particle colliders, gene sequencers, next-gen space telescopes, things human eyes would almost certainly miss.
And beyond the core number crunching and pattern finding, AI is also streamlining the human element of research, correct?
Absolutely. The research highlights the rise of AI co-pilots for scientists. These tools are streamlining everything from literature search and synthesis, helping researchers stay on top of the overwhelming flood of publications, to helping formulate hypotheses, even automating parts of the experimental design process. It's about taking the painstaking, often repetitive work that might take a human graduate student months and potentially reducing it to minutes. This frees up the human researcher to focus on the higher-level conceptual breakthroughs and, critically, the experimental validation.
Okay, that covers how AI helps science. Now let's flip that, because you said it's mutual. How is research in these fundamental sciences, MPS, actually improving the AI models themselves, making them better, more reliable?
This is perhaps the most critical aspect, and one that often gets overlooked in the general hype. MPS research is directly driving better, more robust, and ultimately more trustworthy AI. The research team identified 3 core areas here. 1, physics-informed AI. This is a really big one. It means incorporating fundamental physical laws, things like symmetries, conservation laws like conservation of energy or momentum, differential equations that describe physical processes directly into the AI model's architecture. This doesn't just improve predictive accuracy, it acts as a powerful constraint, ensuring the model doesn't produce physically nonsensical or impossible results. That's absolutely critical in fields like fluid dynamics, climate modeling, or material science. 2, improving efficiency and reducing data dependency. Unlike a lot of consumer AI that thrives on massive data sets, MPS fields often operate in what's called a small data regime. Getting high-quality experimental data in materials science or particle physics can be incredibly expensive, time-consuming, and resource-intensive. This forces MPS researchers to develop highly data-efficient algorithms methods that can learn effectively from limited examples. These innovations then often trickle back into the broader AI ecosystem, benefiting everyone. And 3, rigorous uncertainty quantification, or UQ science, demands rigor. Researchers in MPS are developing sophisticated methods to transform AI systems from black boxes into transparent scientific tools. This means ensuring that every prediction the AI makes comes with a provable, measurable degree of uncertainty or a confidence interval. Science simply cannot afford guesswork. It demands knowing the error bars.
That connection between fundamental science and better AI is really crucial. It also brings us back to a key point about all these advanced systems. They require massive resources, not just intellectual horsepower, but physical infrastructure and energy. We've covered the amazing leaps in digital and physical capabilities, but these systems need huge amounts of power and the hardware to run on. Before we dive into those costs and the very real safety challenges that come with scale, we want to quickly hear from you, our listeners. If you're finding this insightful on YouTube, please do take a moment to like this video, subscribe to Tomorrow Unveiled, and maybe consider hitting that new hype button. Apparently it helps us reach more viewers. And of course, make sure you turn on notifications so you never miss an update on the future. And if you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and perhaps a review for Tomorrow Unveiled. It genuinely helps us reach new listeners who are curious about these topics. Okay, so infrastructure. Let's talk about the hardware race that's enabling this whole autonomous future. The computing demands are clearly so enormous now that the infrastructure itself has become a major strategic geopolitical asset.
It really has. The scale is difficult to comprehend sometimes.
Yep.
And the sources this week revealed a truly historic and strategically significant geopolitical move.
Right.
This massive Blackwell GPU supply agreement between NVIDIA and South Korea. The deal reportedly commits over 260,000 of NVIDIA's latest Blackwell GPUs. That is a staggering number for a single nation commitment, especially for cutting-edge chips.
260,000 GPUs. Why is South Korea making such a massive strategic investment? What does that actually do to their national capabilities in AI? It's completely transformative. The research indicates this agreement will dramatically expand South Korea's existing AI GPU infrastructure, currently estimated around 65,000 units, to well over 300,000 total units. This is a very clear, very deliberate move towards establishing what's being termed sovereign AI. That means national AI infrastructure controlled domestically, ensuring national competitiveness and, crucially, independence in critical AI fields like advanced robotics, smart manufacturing, and national security applications. The report suggests these chips are being allocated strategically across major conglomerates, cloud providers, and the government itself for building out this sovereign infrastructure.
And are we seeing immediate, tangible investments being made based on this supply chain certainty, particularly in that physical AI sector you mentioned? We are, yes. The standout example highlighted in the research is the Hyundai Motor Group. They're establishing what they're calling an AI factory. And it's powered by 50,000 of these new Blackwell GPUs that represents an estimated investment of around $3 billion just for the compute. This facility is specifically dedicated to physical AI development, smart manufacturing processes, autonomous vehicle technology, and critically, general-purpose robotics research, all fueled by massive real-world data collection and simulation capabilities enabled by this hardware.
So the trend seems unmistakable. Nations are now treating advanced AI infrastructure, the actual physical chips, as foundational strategic assets, on par with investing in semiconductor fabrication plants or national telecommunications networks. It feels like an unambiguous race for sovereign AI capability is underway.
Exactly. That's the clear signal from the data. This infrastructure is what fuels the entire autonomous agent revolution we've been discussing.
Yeah.
But it brings us right back to that challenge we touched on earlier, that 16% safety overhead and the overall energy footprint. It is soaring. Just training one of these massive models like GPT-4 is estimated to have cost something in the realm of $100 million. That level of energy consumption and cost raises serious questions about sustainability and scaling. We have to address the efficiency challenge.
That kind of computational cost does seem clearly unsustainable if we want to scale these capabilities globally and equitably. What solutions are being prioritized, according to the research team, to tackle this colossal efficiency problem?
The research emphasizes it's not a single silver bullet, but rather a multifaceted approach to achieving more cost-efficient computing. First, there's a strong push towards prioritizing data-efficient methods, moving away from the default assumption that you just need to throw more data and more compute at every problem. This is obviously critical for scarce scientific data, as we discussed, but it's also relevant for enterprise data, where often the quality and structure of the data matter more than sheer quantity. Second, there's increasing adoption of smaller, more structured models. And related to that, using techniques like model distillation.
Model distillation. Can you explain that briefly?
Sure. It's essentially training a smaller, faster, more efficient student model on the outputs, the predictions, or decisions generated by a much larger, more powerful teacher model. You try to capture the essence of the big model's capabilities in a much more compact form.
What are the trade-offs there? With these smaller, distilled models, do you sacrifice a lot of accuracy or capability?
Often, yes, you might sacrifice some of the absolute top-end performance on certain benchmarks, but what you gain is enormous speed, much lower latency, and significantly reduced computational cost. This makes the distilled models viable for real-time applications, deployment on edge devices, or situations where cost is a major constraint. It's a strategic trade-off.
Makes sense. And looking beyond traditional silicon chips, are there other hardware approaches being explored?
Yes. The third pillar mentioned in the research is actively exploring emerging computing paradigms, specifically as specialized AI accelerators. Talking about things like neuromorphic computing, which mimics brain structures, photonic computing, using light instead of electrons, and even quantum computing for certain types of AI problems. These specialized hardware types hold the promise of handling specific AI calculations like matrix multiplications or optimization problems at potentially a fraction of the energy cost of current GPUs. But it's important to note they are still maturing and face significant challenges related to manufacturing scale, programming models, and standardization.
Okay, efficiency is key, but now we absolutely must transition to the urgent risks, particularly the newly identified safety risks associated with multimodal AI. Just be clear, when we say multimodal AI here, what precisely are we defining?
Good question. In this context, multimodal AI refers specifically to systems that can process and generate both text and image input-output simultaneously. So a user might provide an image along with a text prompt, and the AI has to understand and reason about both layers of information together to generate a response, which might also be text or even a modified image. The critical vulnerability that our research team found, and this was corroborated through extensive red teaming exercises, is that these models are susceptible to entirely new forms of attack, specifically by embedding harmful textual instructions inside otherwise benign-looking image files.
Wait, embedding text instructions inside an image file, and the AI reads that hidden command. How on earth does that bypass the safety filters we usually rely on?
It exploits a fundamental architectural capability, maybe even a necessity of the multimodal model. Its ability to process the entire input field, including the pixel data of the image, not just the visible text prompt that the user types. Traditional content filters are usually laser-focused on analyzing the visible text for harmful language, or maybe doing basic image recognition for known harmful visual content. This technique cleverly bypasses those filters because the malicious instructions are hidden within the image's pixel structure, often in a way that's invisible to the human eye or looks like random noise. The image itself might look perfectly harmless, but the underlying neural network, trained to extract meaning from pixel patterns, recognizes the embedded text pattern and then proceeds to generate dangerous outputs without any obvious trigger in the user's visible prompt.
That is deeply concerning. It's like a hidden message directly to the AI's core, bypassing the guards at the gate. What kind of corroborated high-stakes, dangerous outputs were actually identified in the research using this method?
The research highlights some extremely serious and immediate risks. These outputs were corroborated during red teaming. They include the generation of child sexual exploitation material, CS, which is obviously horrific, and critically, the generation of hazardous CBRN information.
CBRN, for our listeners, can you briefly define what that means in this context? And why is the autonomous generation of this specific type of knowledge considered so high stakes?
Sure. CBRN stands for chemical, biological, radiological, and nuclear material knowledge. The immediate danger here isn't that the AI is somehow physically building a weapon. It's that it can autonomously synthesize and generate highly accurate, potentially step-by-step instructions or blueprints for creating dangerous materials or processes. Information that previously required highly specialized, often classified or obscure knowledge to compile from multiple sources. Because these advanced agentic models can access and synthesize vast amounts of scientific literature, technical manuals, potentially even leaked documents, they could theoretically create detailed, dangerous instructional guides on demand, prompted by these hidden commands.
That possibility alone is terrifying. Given that level of risk, what are the necessary mitigation strategies? What needs to be done to address these novel, multimodal vulnerabilities?
The required proactive response based on the research findings seems to be built on three essential pillars. First, continuous automated stress testing. This means constantly, automatically simulating adversarial attacks like this hidden text method, trying to find these vulnerabilities before malicious actors do. You can't just test once before deployment. Second, implementing much more sophisticated context-aware guardrails. These safety layers need to be able to understand the nuances of multimodal inputs, looking for inconsistencies or suspicious patterns across both text and image data, preventing the system from blindly executing commands where the input trigger might be hidden or obfuscated. And third, mandating model risk cards. These are essentially transparency documents, like nutrition labels for AI models. They need to clearly communicate specific known vulnerabilities and limitations, like this potential for multimodal exploit risk, to developers, users, and regulators.
Okay, so continuous testing, smarter guardrails, and transparency. That makes sense. Beyond these critical safety issues, we also need to consider the ethics surrounding generative content, especially as these agents move more assertively into creative fields like music. The legal and ethical landscape is still very much catching up.
Indeed it is. And we saw a very significant development on this front just this week, highlighted by the research team. The announcement of a strategic partnership between Universal Music Group, UMG, and Stability AI. Now, UMG, as you probably know, has historically taken a very, very aggressive stance on protecting artist rights against the unauthorized use of their music for training AI models.
Right, they've been quite litigious. So what's the strategic goal of this specific partnership, given that history? Is it a change of heart or something else?
The stated primary goal seems to be about establishing industry standards for responsible AI music generation, working together on a framework. This means figuring out practical ways to ensure proper attribution for artists, establishing fair compensation mechanisms for artists whose work informs or inspires AI-generated music, and critically, committing to using licensed, ethically sourced data for training future music models. And this move is particularly important. The timing isn't accidental. It follows closely on the heels of UMG reaching legal settlements with another AI music generator over copyright infringement issues.
Ah, okay. So this partnership signals perhaps a major shift, moving towards licensed data and ethical development becoming not just a nice-to-have or a regulatory compliance hurdle, but actually a competitive differentiator, a necessary cost of doing business if you want to work with major players.
Precisely. That's the interpretation supported by the research context. It shows that major industry players like UMG are recognizing that a framework built on ethical practices and fair artist compensation is probably essential for creating commercially viable, legally sound creative AI products in the long run. If your AI model is built on shaky legal or ethical ground, It becomes very difficult to insure, to license, or to get adopted by major enterprise clients or platforms. Responsibility is becoming table stakes.
This has been an incredibly dense week, or rather, 7 days of breakthroughs condensed for us. Let's try to bring it all together.
The key transformation, the thread weaving through all these developments we've discussed, seems to be this fundamental transition. AI is moving beyond being just a tool into becoming autonomous, reasoning infrastructure that's embedding itself across seemingly every sector. From securing our data and automating enterprise workflows to generating scientific hypotheses and even starting to walk around in the physical world via robotics.
Absolutely. And if we try to connect all these threads from our sources from the research team's compilation, I think 4 key takeaways really stand out as essential knowledge for anyone trying to understand where this is heading. First, agentic AI maturity is here. Autonomous systems are moving rapidly from the realm of theoretical research into essential production infrastructure. That coordinated simultaneous launch of enterprise agentic platforms by Google, Microsoft, OpenAI, that confirms this isn't speculative anymore. It's happening now. Second, robotics is approaching consumer scale potential. General-purpose humanoids like Optimus, with those ambitious mass production targets and that aggressive price point, are likely to hit commercial markets, probably starting in manufacturing and logistics within the next 1 to 2 years. This could accelerate impacts on labor and productivity far faster than previous generations of specialized, single-task robots ever did. Third, safety and ethics are becoming differentiators. We're seeing AI developers actively using advanced AI models like ARDVARK to strengthen security from within. And we're seeing strategic partnerships like the UMG Stability AI deal explicitly focused on building ethical frameworks and using licensed data. This strongly suggests that responsible, transparent, and robust development isn't just good PR, it's becoming a critical competitive advantage in the marketplace. And fourth, the sovereign AI race is on. Nations are clearly viewing advanced AI infrastructure, owning the physical chips, the compute capacity as a foundational strategic asset, absolutely essential for future economic competitiveness and national security. That historic NVIDIA South Korea deal and the massive investments in national AI factories are prime examples of this intensifying geopolitical race for compute sovereignty.
Those are really crucial takeaways. Agent maturity, robotics scaling, safety as advantage, and the sovereign AI race. We genuinely love hearing your thoughts on all this. Whether you're watching on YouTube or listening on your favorite podcast app, please leave a comment and let us know what you think about this rapid shift towards autonomous agents. What does it mean for your industry, for your work, for society?
And maybe here's a final provocative thought to leave you with. Building specifically on that VRSCI project where AI agents were generating new scientific ideas. The sources reveal that AI is now capable of autonomously designing novel research ideas at an unprecedented, almost overwhelming rate, potentially near infinite. However, the human challenge remains immense. Synthesizing those raw ideas into original, coherent, publishable research abstracts is one hurdle, but the much bigger one is physically validating the concepts through rigorous experimentation in the real world. Now consider this. If AI continues to generate, say, 100 times more potentially novel research ideas than the entire global scientific community can collectively manage to investigate, execute, and validate a process, which itself is incredibly expensive in terms of human labor, resources, and even compute. Remember that 16% safety validation overhead. Then the primary bottleneck in scientific progress might soon shift. It won't be the generation of new ideas. AI might flood us with those. It will be the entirely new challenge of human oversight, critical assessment, experimental validation, and the integration of that knowledge. So what happens when the truly scarce resource is no longer computational power or data, but rather the finite collective human attention required to sift through, prioritize, and ultimately turn AI-generated novelty into validated, trustworthy knowledge? That's something to think about.